If you want to build something that runs on the web, and especially if it involves 3D graphics, you're just going to ship a massive binary to the user.
Yeah, you pull in a massive framework, maybe a full game engine, and suddenly your basic hello world is a 50 megabyte download.
It's wild. It feels like bloat is just the tax we pay for developer convenience nowadays.
It really is. We just keep layering libraries on top of libraries, and eventually we completely lose track of what the hardware is actually doing.
Exactly. But today, we're doing a deep dive into a project that completely rejects that whole premise. We're looking at Zigon.
Which is a fascinating piece of software.
It really is. On the surface, it's a procedural generation engine, so it makes 3D terrains and dungeons, but the engineering under the hood is the real story here.
Right, the tech stack is what makes it special.
Yeah, and for this deep dive, we're pulling directly from the Zigon GitHub repository by developer Jussi Falbers, along with the Zig language release notes and their official documentation on C interop.
Because it's built using the Zig programming language, uses Raylib for rendering, but, and this is the weird part, it allows you to script everything in Python.
It is a really specific, arguably strange combination of tools, but here's the kicker that got my attention. It can deploy a fully interactive 3D world to a web browser, and the file size is 386 kilobytes.
Which is honestly smaller than the banner image on most websites you visit today.
Right, so the mission for you listening to this deep dive today is to figure out how that is even physically possible.
It's a classic case of trying to get the best of both worlds in engineering. Or at least, that's the promise they're making.
Well, let's test that promise.
Yeah.
Because normally when you mix a fast systems language like C or Zig with a slow scripting language like Python, you just end up with a mess of glue code.
Oh yeah, it becomes a nightmare to maintain.
So what is the actual architecture of Zigon? How does it avoid that trap?
So Zigon operates on this very strict hybrid model. The core philosophy in the documentation is native performance where it matters and scripting flexibility where it helps.
Which, I mean, that sounds great on a slide deck, but what does that actually mean in the code base?
It means strictly separating the engine from the game logic. So all the heavy lifting, the terrain generation, mesh construction, the vertex math that is entirely written in Zig.
And Zig is a systems language, so it compiles down to raw machine code.
Exactly. It creates a binary that runs directly on the hardware, no virtual machine, no interpreter, just bare metal speed.
And then for the visuals, it wraps Raylib.
Right, which is a C-based library that's known for being incredibly lightweight compared to a giant like Unreal or Unity.
Okay, so you have this blazing fast engine, but then they bring Python into the mix. Why do that? If you're so obsessed with performance, why introduce a notoriously slow scripting language?
It's all about the iteration loop. If you write your entire game logic in Zig or C++, every single time you want to tweak the height of a mountain or change a spawn rate, you have to recompile the whole program.
Right, you get stuck in that compile, wait, run cycle.
Which kills productivity. So by exposing a Python API, Zigon lets you write all your gameplay rules in Python.
Because Python is great for logic, even if it's slow at math.
Exactly. The Python script just acts like a manager. It tells the Zig engine what to do, and the Zig engine executes the heavy lifting at native speed.
So it's basically using Python as a remote control.
Precisely. It uses the SIGtypes library in Python to send commands straight to the compiled Zig shared library.
Okay, I definitely want to get into the performance numbers on that because the benchmarks in the repo look a bit controversial. But before we get there, let's talk about what this engine actually generates.
The terrains and dungeons.
Yeah. How does it just make a mountain? Because it's not just random noise, obviously.
No, true random noise just looks like TV static. It's completely unplayable. To get natural-looking terrain, Zigon uses something called fractional Brownian motion, or FBM.
Break that down for us a bit.
Sure. Imagine you want to draw a realistic coastline. You start with a big, smooth, wavy line that is your first octave. It gives you the general shape of the landmass.
Okay, octus.
Then you add a second curve on top of that. This one has more wiggles, but it's smaller in scale. That's your second octave. Then a third, even wigglier, even smaller line.
So you're just layering detail on top of detail.
Exactly. FBM is mathematically summing up these layers of noise at different frequencies. And in the Zigon code, this is controlled by two main variables, lacunarity and persistence.
I saw those terms in the source. They sound like something out of a sci-fi novel.
They do, but they're pretty intuitive once you use them. Lacunarity controls the frequency jump between the layers, basically how much smaller the details get each time you add an octave.
And persistence.
Persistence controls how much roughness or amplitude is preserved. So if you have high persistence, those tiny fine details are very strong and you get jagged, rocky peaks.
And low persistence.
The details fade out faster, so you get smooth, rolling sand dunes.
And because this is all running in Zig, it's calculating that math for every single vertex on the 3D mesh.
Millions of times per second without breaking a sweat.
That's crazy. So what about the dungeons? Because the documentation mentions wave function collapse, or WFC. And I've seen that used in some indie games, but it is notoriously hard to run efficiently.
Oh, it is. WFC is essentially a constraint satisfaction algorithm. The best way to think about it is like a jigsaw puzzle, but the pieces haven't been cut yet.
Okay.
You start with a grid where every single tile could theoretically be anything, a wall, a floor, a hallway.
So that's the wave part. All possibilities exist at once.
Right. Then the algorithm observes one tile and commits to it. It says, okay, this tile is definitely a floor tile.
Makes sense.
But now, because of that choice, the tile immediately next to it cannot be a solid rock wall, because the rules state that floors have to connect to other floors or doors.
So the possibilities for the neighboring tiles collapse.
Exactly. And that constraint propagates outward across the entire grid like a ripple.
But what happens if it gets stuck?
That's the hard part. If the algorithm backs itself into a corner, say it needs to place a door, but the only valid neighbor left is solid rock, it has to backtrack. It undoes its previous choices and tries a different path.
And that backtracking is the really expensive part, computationally speaking.
It's incredibly expensive. If you tried to write a WFC solver with backtracking in pure Python, your game would just freeze for several seconds every time you generated a level.
Which is why Zigon offers 6 different dungeon archetypes right out of the box.
Yeah.
Right? Like rooms, rogue, cavern, maze, labyrinth, and arena.
Yeah, and it generates all of them instantly because the solver is written in Zig.
Which brings us to those benchmarks. The Zigon team ran a comparison where they generated a 256 by 256 terrain grid. That's roughly 65,000 data points.
Right, and they tested it across pure Python, NumPy, and then native Dig.
Let's look at these times. Pure Python took 1,919 milliseconds, so almost 2 full seconds.
Which is totally unplayable for real-time generation.
Right. Then they tried NumPy. And for anyone listening who doesn't know, NumPy is the gold standard for math in Python. It's heavily optimized and actually written in C under the hood.
So you would expect it to be very fast.
And it was. It took 18.9 milliseconds. That is 100 times faster than pure Python.
But then they ran the exact same generation in Zigon, 12.7 milliseconds.
Okay, hold on. I actually need to push back on this a little bit.
Yeah.
18.9 milliseconds versus 12.7. We are talking about a difference of literally 6 milliseconds. Does that actually matter in the real world?
It absolutely does.
And secondly, why is there a difference at all? If NumPy is written in C and Zig is roughly comparable to C in speed, shouldn't they be effectively identical?
That is the critical question. So to your first point, yes. 6 milliseconds matters immensely in game development. If you are targeting 60 frames per second, your entire budget for a frame is about 16 milliseconds.
Oh, right.
NumPy already blows the entire frame budget just doing the math. Zigon does it in 12, which leaves you a few milliseconds to actually render the graphics to the screen.
Okay, fair point regarding the frame budget. But why is NumPy slower if it's written in C?
Because of the boundary tax. NumPy is fast internally, but it still has to talk to the Python interpreter. It has to create Python objects to wrap the math results so your script can actually read them. It has to handle reference counting for the garbage collector.
So Zigon running natively is just moving raw bytes around in memory.
Exactly. There is no middleman. It's direct memory access.
So it's just the overhead of NumPy trying to be a friendly, safe Python library.
Precisely. And you see this even more clearly in the memory usage stats. This was the part that genuinely shocked me when I read the repo.
Let's hear it.
For a 128 by 128 terrain, Python and NumPy used over 3,200 kilobytes of RAM. Zigon used 64 kilobytes.
That is a massive difference. I mean, 3 megabytes isn't a lot for a modern PC, but 64 kilobytes is, well, that's Commodore 64 territory.
It really shows how incredibly inefficient our modern tools are. Python allocates memory for objects, garbage collection tracking, massive headers. Zig just says, I need an array of floats, and it takes exactly that amount of space. No more, no less.
There are no hidden allocations.
None. And that efficiency compounds, especially if you're trying to run this on a low-end mobile device or, heaven forbid, inside a web browser.
And that is the perfect transition to the web deployment aspect, because this is where Zigon really flexes its muscles.
The 386 kilobyte number.
Yes. Walk us through this, because usually if I export a very basic game to the web using Unity, I am sitting there waiting for a 30 to 50 megabyte download.
Yep.
Even Godot, which is widely considered to be a lightweight engine, is usually around 15 to 25 megabytes just for the base engine WebAssembly. How on earth is Zigon getting a full 3D terrain engine into 386 kilobytes?
Is it stripping out features?
Yeah, what's missing?
Nothing is missing. It's not stripping features, it's stripping the environment. When you deploy a typical web app today, you are usually deploying a massive runtime along with it.
Like Electron.
Exactly. If you use Electron, you are literally bundling an entire Chromium web browser into your app. If you use Mscripton to port C++ code to the web, you're deploying a heavy emulation layer that pretends to be a Linux file system just so the C code doesn't crash.
So it's the glue code problem all over again.
Right. But Zigon bypasses all of that by using Zig's native WebAssembly, or WASM support. It ships with something called Raylib.
What does that do?
Instead of emulating a full operating system, Raylib only includes the absolute bare minimum system calls needed to talk to the browser environment.
So it completely cuts out the fake OS layer.
Completely. And on top of that, Zig is incredibly aggressive about dead code elimination, meaning if you don't use a specific function from the Raylib library, Zig doesn't even compile it into the final binary. It whittles everything down to just the exact code paths Zigon actually executes.
That is so impressive. But, let's zoom out to the developer experience for a second. Because all this performance is amazing, but if the toolchain is a nightmare to use, nobody's going to adopt it.
True. We've all spent days fighting with makefiles and cryptic linker errors.
Exactly. But this is where Zig actually makes its strongest case as a modern replacement for C. The documentation talks a lot about its C interoperability.
Which is usually the most painful part of systems programming.
Right. Normally making two languages talk to each other is awful. You have to write all these manual bindings.
Yeah, if you want to use a C library in Rust or Python, you have to manually redefine all the C data structures in your new language. And if the C library updates and changes a struct, your whole project breaks.
And Zigon uses Raylib, which is a pure C library. So how did Josie Falbers handle that without writing thousands of lines of wrapper code?
Zig has this almost magical built-in feature called @import. You literally just point the Zig compiler at a standard C header file, and it understands it.
It just reads the C code.
It reads it and converts all the C macros and types into native Zig types automatically, right at compile time.
Wait, so you don't have to write any wrapper code at all?
Zero. You just import the header and call the C functions exactly as if they were native Zig functions. It works because the Zig compiler actually includes a full C compiler, Zig CC, baked right into it.
That sounds incredibly convenient. But what about cross-compilation? Because that's the other huge pain point. If I'm working on a Mac and I want to build a version of my game for Windows, normally I need to install a totally separate tool chain or spin up a Windows virtual machine.
Correct. You usually have to download these massive sysroots, which are basically giant folders full of Windows-specific header files and dynamic libraries, and it's always a nightmare of version mismatches.
And how does Zig solve that?
Zig actually ships with the raw source code for the standard libraries of all the major operating systems. It has glib for Linux, muzzle, Ming for Windows, all built in.
So when you build for a different OS city,
when you run the build command and set the target to Windows, it literally compiles those standard libraries from source on the fly for that specific target architecture.
it compiles the entire standard library from source.
Yes. It doesn't rely on whatever pre-built binaries happen to be sitting on your host machine. This guarantees that if a project builds on your laptop, it will build and run exactly the same on the target device.
Which explains how Zigon can have that single command deployment feature they advertise.
Exactly. One single build command produces the native desktop app, the Python library bindings, and the WebAssembly bundle all at the same time, regardless of what operating system you are actually developing on.
That is a massive workflow improvement. It really feels like the Zig team just looked at everything that makes C and C++ development miserable. The makefiles, the headers, the cross-compiling, and just fully automated it.
They did. And there is one more language feature we have to touch on because it really explains how they get that tiny WASM file size, comp time.
I saw that mentioned in the build flags, like when you set the map size or the dungeon type.
Yeah. In most programming languages, compile time just means the process of turning your text into a binary. But in Zig, comp time is a keyword that allows you to run actual arbitrary code during the compilation process itself.
Give me a concrete example of why that matters for a game engine like Zigon.
Okay, take the map size grid. Let's say you configure it to be 512 by 512. In a normal C program, the compiled code would look like a loop, run from 0 to map width, and the CPU has to actively check, is my current variable equal to map width? Every single time it loops.
Which invokes branch prediction overhead.
Exactly. But with comp time, the Zig compiler knows that the map size is permanently 512 for this specific build, so it can just unroll the loop entirely. It can hardcode the exact memory offsets. It literally eliminates the if statements from the final binary because the answer is already known.
So it's not just optimizing the code, it's dynamically rewriting the logic based on your configuration before the program even runs.
Correct.
Yeah.
And that is a level of hyper-optimization that is incredibly difficult to achieve in other languages unless you resort to really ugly, unreadable macros.
So bringing this all back to Zigon itself, we have a terrain engine that is lightning fast. It's tiny, and it runs natively everywhere from a desktop to a web browser.
It's a brilliant technical showcase.
It really is. But is it more than just a cool tech demo? What is the actual takeaway here for the average developer listening to this?
I think Zigon acts as a really powerful proof of concept for a totally different way of building software. We have been stuck in this siloed mindset for years where web automatically means JavaScript, system means C++ or Rust, and data means Python.
And we just accept the massive bloated bridges we have to build to make them talk to each other.
Exactly. Zigon proves that a modern toolchain like Zig can actually collapse those distinctions entirely. You can have the raw, bare metal performance of C, the universal reach of the web through WASM, and the ease of scripting in Python, all bundled into a package that could literally fit on a 1990s floppy disk.
It really challenges the assumption that modern software has to be massive to be powerful.
It absolutely does. When you see that a single developer can build a fully interactive 3D procedural engine in 386 kilobytes, it really makes you look at that 200 megabyte chat application sitting on your desktop and ask, what is all that space actually doing?
Yeah, it's suffering-oriented programming versus bloat-oriented programming.
We could definitely use a little more discipline in how we ship code.
Seriously. And, it makes you wonder, if we can strip away the bloat this effectively for a 3D engine on the web, what else is possible? What if we took this zero bloat philosophy and applied it to our actual operating systems? Imagine an OS built from the ground up with this kind of comp time optimization and zero hidden allocations.
That would be a completely different computing paradigm.
It really would. Well, if you want to inspect the code for yourself, and I highly recommend at least looking at the build.zig file to see how that cross-compilation magic is actually set up, check out the Zigon repository by Joseph Albers on GitHub. It is a fascinating glimpse into what a post-C programming world might look like.
Absolutely worth the read.
Thanks for diving deep with us. We'll see you on the next one.